at that. Okay, I am now recording. So we left off at intent-based networking. Now we're going on. So one of the important products that includes intent-based networking is Cisco's Digital Network Architecture, or DNA. And the point of DNA, the big thing, is it basically applies one network plan to the entire network. Whatever your operational plans are, it applies it everywhere. So the old idea, draw a picture. The old idea is you had a bunch of stuff inside your network and you regulated how it all works. I'm going to draw some kind of hierarchical model here from, clients to various, data center type things in the back. And you regulated how all those components worked, right? Well, in the cloud model, in the Cisco, digital network architecture, well, before I get into that, let's just mention that keeping all of this stuff working the way you want to is a bit of a headache in various ways, okay? Because anything that happens in one part of the network could potentially have some effect on other parts of the network, right? Different groups of clients are interacting. These data centers are potentially interacting. So the old hierarchical model that we'll cover briefly, yeah, it didn't work maybe as well. It worked well to start with, but as database systems became more complicated and these database hardware components needed to communicate with each other, you got a lot of that east-west traffic instead of just north-south traffic like we talked about last week. Okay, so one of the things that businesses did to deal with that is they came up with something called a network approach, software-defined networking, that essentially put these components in the middle. It basically had some centralized manager that would create essentially a two-way hierarchical network so that everything that happened went through this centralized point, and that way you could regulate the flows better. You could, even if there was a lot of what would be east-west transfers, they would still go back down to this centralized manager. And you'd be able to achieve the plan of separating traffic flows through this sort of two-way hierarchical thing. So some traffic will go this way, some traffic will go that way, and some traffic will go all the way through the centralized manager, right? Like traditional north-south. But without getting too deep into the details of it, setting up this centralized manager and making it work the way it's supposed to is a big headache, right? So this sort of thing, it's one of those, sounds great on paper, but for a lot of businesses, it was more trouble than it was worth. But the basic idea is good. It's just businesses had a hard time implementing it. So bring in Cisco, and then you have this possibility where this is your business. Okay, and here's Cisco over here, and the good people at Cisco, for a financial consideration, are willing to essentially provide this service to you. So we blow up that software-defined networking type system. Okay, here's the connection between your stuff. Here's basically your data centers, however they're set up. It's going to manage all this part of optimizing these traffic flows for you, because Cisco is good at that. Cisco's better at it than you guys are. And the business, meanwhile, basically has one data faucet on the wall that all of their stuff goes through. So the business has access to this centralized manager, right? It can see into there. I'm going to draw a little line. Ooh, that's not what I wanted. This is what I wanted. I want it to be stretchier. Okay, so business can see into the centralized manager, but doesn't have all the headaches of actually managing everything. Okay, so you can see how stuff is going, you can change your policies, but you don't have to struggle with all the implementation details that maybe your business isn't really that good at doing. Okay, so this is essentially what's going on with Cisco DNA. It's taking all this stuff that was software-defined networking under your own roof, and they're taking the side of it that used to go from, so here we have, damn it, typing is hard. Typing is hard. So clients, servers, they're taking all the headaches, they're managing the headaches for you. Okay, that's the core of what they're doing here. Now, what do we say? So this is DNA, Unified Automated Manager for an enterprise's entire application stack. So that means all the stuff the enterprise is doing, Cisco is going to manage all those applications for you. And this is, if you think about it, a natural extension of the cloud model. So ordinary cloud, you have applications hosted up in the cloud, but the data flows aren't that closely regulated. Here, Cisco is taking on, first there would be this part, which I'm going to circle. This part would be ordinary cloud, right? Your servers are all effectively running up in the cloud doing stuff, but then Cisco is going to add on this extra part, the centralized data manager, so you can apply whatever policies you want and ensure that the traffic flows are arranged down to the clients for whatever kind of quality of service you want to achieve. Okay, so that's why it's a natural extension of the cloud model. Now, the selling points on this, number one, the entire network is visible through the same control center dashboard application. Basically, you can look at this centralized manager and see exactly what's going on with the network. Whatever you want to track, yeah, you can track it through there. It's all in one place. Number two, security, quality of service policies can be automatically and uniformly enforced throughout the network. Essentially what happens, if you have a network that's all under your own roof, it can be a bit of a problem. The problem is sometimes applications running in one part will affect what's downstream of them. So let me give a quick example of that. Imagine if you have, very simple example. Okay, so you have, kind of looks like Purina dog chow. Okay, so server 1, server 2, and down here, client 1, client 2. Now, depending on what's going on in the network, the ability, since it's all going through the same components, since it's all going through some switch here, if server 1 and client 1, if there's nobody else using the system, everything's good, right? There's plenty of capacity in the system for them to do what they want to do. But suppose client 2 and server 2 are really busy, right? Suppose, in fact, it's not just one client, but a whole cluster of clients here, and they all have high priority, and they all, take a lot of data. So I'm going to say clients 2 plus, right? Because there's whoever else, and maybe they're pushing so much data through with a higher priority level that it blocks everybody else. So basically client 1, he can't get enough data to do his applications the way they're supposed to work. So this is a problem, right? You'd like to have some way to regulate that, because maybe, the rules you came up with for prioritizing these applications, yeah, maybe you still want this guy to get what he needs under some cases. So this is potentially a problem that even in a hierarchical network where traffic flows are regulated, yeah, things can still get busy. So that's the sort of problem. Now, what this means in practice in terms of quality of service management, it means this. It means quality of service for client 1 really does depend on what the other clients connected to part of the same system are doing. And that means it's more difficult to test the system because it's harder to cover all those cases, right? You might come up with some standard baseline expectation of, oh yeah, as long as this side isn't too busy, everything's going to be great for client 1. But that's not a guarantee that it's always going to be that case. And of course, this is a super simple example, right? This is a very, very simple example. You can have many more servers and components and clients and traffic overflows. Even for a simple example, you can start to see how, yeah, maybe there's some dependencies built into the testing. But in a real, very complicated enterprise system, there's all sorts of troubles in. So managing quality of service is actually potentially difficult. But again, Cisco is going to do that. Cisco is going to say, okay, in this centralized manager, in the centralized manager here, they can make sure that all the outflows going here, they know which clients they're going to, they know which applications are being run. So whatever policies you want to implement, Cisco can make sure that they are implemented correctly implemented, correctly and uniformly through the whole system. Because why? Because Cisco is running basically everything through this whole system. All of your data is going through this one choke point back into your organization. Okay. So, and the net result of that, because testing is easier, you can, cover whatever, make whatever assumptions you want and impose whatever policies you want and actually have them be, enforced correctly. You can deploy workable applications much faster. It's easier to go through the testing process, make sure that what you expect to happen is what actually is going to happen. So when you deploy the applications, they're going to work the way you think they're going to work. Okay. And now if anybody's interested, again, link here, what Cisco calls the network intuitive, which is, this kind of system setup. That's what they're selling on that. They're basically saying, you know what, we're going to take away all these management headaches for you. And the net result is you will be able to run your applications faster and better and deploy them sooner. Okay. Now, how revolutionary is this? Well, depending on who you ask, right? If you're asking the guys at Cisco, they're going to say, yeah, this is the biggest thing since sliced bread. This is the biggest thing since cloud. It's great. It's going to solve so many troubles. On the other hand, yeah, maybe not. I mean, it's still a product. It's viable. It's out there. It's used. For the right business, it's a great tool, but for the wrong business, not so much. Let's see if I can pull this. Okay, so engineer's perspective about Cisco DNA. So here they say, yeah, this is the wrong article. The links don't always incorporate in the slides the way they're supposed to. Let's see. Oh, because I clicked the wrong one? Oh, that's strange. I don't know why it's doing that. Cisco invents. All right, I'm going to do it the correct way. Let's lift this and see if I get it. Okay. There we go. Cisco reinvents SDN, software-defined networking, and the market yawns. So here we go. Cisco, this is from a couple years back, so 2017. Tuesday, Cisco announced a new plan to make its networking technology more programmable and software-driven, but does the market care? In San Francisco, company gathered analysts, media, customers at a glitzy marketing event and to announce the biggest innovation in the past decade, and then its share price fell. Okay, so anyway, not everybody is super impressed with this. It is, my opinion, generally, it's innovative. There are some interesting things in there, but it's part of what's just general incremental drift. So it's going to change the way people are doing things. What we have here is networking as a service, which is a growing sector of the IT world. But here's the thing. Big picture stuff, it's always towards letting the machines do more of the work because the systems are more complicated. As the systems get more complicated, it gets harder and harder for humans to do anything more than just manage the big picture details, right? The humans don't really want to go deep down into the guts of the machine and tweak everything while it's running. It's just not feasible. The systems are too complex. So growing numbers of devices and applications driven by Internet of Things make manual guidance hopeless, right? The network systems are just too big. No matter how good you are at what you do, the ability to change any of these things in real time for an ordinary human is pretty much hopeless. Now, Cisco is not the only one working on this problem, right? Its competitors are doing it too. And so then you get links like this. Cisco launches the network that the new generation might not need anymore. But the general drift of taking control away from humans, giving it more to machines, and having humans just check, yeah, is this system working the way it's supposed to? That makes sense. In an era of growing complexity, there's not really any other way to do it. Okay. So now we'll talk a little bit about network designs, some typical structures, and then at the end we'll get into some related issues about a little bit of nuts and bolts stuff about routing and hardware, stuff like that. Okay, so the basic model that a lot of operations have is what's called hierarchical design. And hierarchical design is essentially built around what are called tree networks. The basic problem, if you have a flat network, it's not scalable. Well, what is a tree network? What is a flat network? Okay, so let's talk. In a tree network, right, which is hierarchical, traffic is separated into groups. So imagine if you have, okay, you have a couple data centers at the top, and they do have connections between them, but those aren't primarily what you use. And you also have clients at the bottom, right? Many clients. And each of them goes through some intermediate layer, right? So up at the top, you have databases. Each one of these application servers is connected to a set of clients. And each one of these is primarily connected to maybe one of these devices, but there are, you know, there is the possibility of connecting to others. Okay. But in a hierarchical system, what happens is that certain traffic flows are going to be dominant. So for example, this one will be one main flow, this will be one main flow, this will be one main flow. There is the possibility for devices to cross over, but basically the main traffic flows are separated. And this provides a more efficient traffic management scheme. Essentially, you have all these flows in parallel. So whatever your capacity is from top to bottom here, you're going to have basically 3 of those running in parallel. You can push through more data. As opposed to if you had everybody in one big tube, yeah, you might have the same amount of data, but it's going to be same amount of capacity, but it's going to be more chaotic. Parts of it will be busy at certain times. You're going to have to throttle some users, not others. Here, the nice thing about this is you can recognize, for example, if one part of the network is consistently busy, you can plan to expand that part and just that part, right? So there are different ways to do it. Maybe you add on a separate parallel channel on the side, or maybe you upgrade your hardware in that so you have higher capacity cable, whatever. Maybe you pick a different set of applications. But the point is, these traffic flows are separate. It's easier to manage quality of service because you get a better idea of what's going on, and it's easier to implement solutions to quality of service issues. On the other hand, if you have a flat network, right, it might look something like this. In a flat network, maybe all of these guys are interconnected, but you still have the basic problem. So these are all of your, I don't know, servers connected to some data center. So what am I missing here? I need a couple more. Okay, these are all of your servers, and maybe each one of these has links to several clients. Okay. And then these devices are all connected to each other. So at the endpoints here, these are all clients. Let's just paste that in a few places. Whoop. Okay, what happens though, the main traffic flows, even though potentially anything can connect to anything else, the main traffic flows are still going to exist. So for example, maybe this set of clients is routinely going through here, okay? And this set of clients is routinely going through here, things like that. And maybe I don't like the way this Zoom interface, every time I bump up against this, it wants to move it. Can I even, I just want to move you off to the side. Why don't you? There we go. Now you're sort of out of the way. There's no really good place to put it though for paint. Anyway, so the issue fundamentally is that all of these traffic flows can potentially interfere with each other. So even though I might set up a carefully calibrated system that works well, any change to one part of the system can cause traffic flows to be rerouted and cause total quality of service chaos. Okay, so the issue with this kind of flat network, yeah, you can still build in all the same components and you'll still have main traffic flows. But if I change something, for example, so that I add on more traffic onto this route, which makes some other traffic push off and keep this other device busier, and then this says, oh, I can't go that way anymore, that's not the best way, so I'm going to push traffic over this way. There's a whole bunch of cascading effects that cause problems that basically you make a change to this network, it can have unpredictable consequences throughout the entire network. So this kind of flat system is pretty dangerous to implement, at scale. It's going to cause you a lot of headaches. Okay. Now, your basic hierarchical design, like I said, built around tree networks. So in this flat network scheme, doesn't scale very well. You make it big, what happens? Any of your network traffic flows, they're going to inhibit other traffic, and they can cause changes to traffic flows which cascade, or if you make a configuration change to the network, again, it can unpredictably affect traffic flows throughout the entire network. On the other hand, the tree network that we saw a minute ago, highly scalable, right? There are, you can set up your routing into separate channels basically, and if you make a change to one, then the consequences are easily understood. Let's see if I can pull this back all the way. Maybe I can, maybe I can't. Good. Okay, so for example, if I add on a few more clients here, maybe this channel gets more busy and I have to segment it somehow, or I have to upgrade some components. But if I make a configuration change, yeah, it's going to be generally pretty easy to deal with. Okay, so that's why we like these tree networks, is because they do better, they handle configuration changes better. Now, Cisco's standard setup for this is what's called a 3-layer campus network model. And there are 3 layers in it called core, distribution, and access. And this basic structure has been around for a long time, like back to the 90s. So if you were to grab some network engineer from like circa 1995 and drop him in 2020, yeah, he'd pretty much know what was going on. It wouldn't be that different that he'd have no idea. I mean, of course, the components are different, the mechanisms are different. He'd look at software-defined networking and say, wow, that's kind of neat, we didn't have that. But this basic hierarchical structure, this has been around for a while. So even though some of these diagrams that I use, they're pretty old, they're still valid. Now, what we have in this basic structure, we have 3 layers. We have the access layer where the ordinary client machines are. And so you can see those are like old-timey 286 machines. The distribution layer, that's basically a boundary between these ordinary users and the core layer. So for core layer, think data centers. And the distribution layer is going to bundle up all these connections. So what you don't want every device on the access layer having to have a separate connection to every device in the core layer. It would be a big headache. So what you want to do is have them all connect to the distribution layer, and then the distribution layer aggregates all that traffic and sends it to the core. That way, for every one of these devices, you just need one connection to the distribution layer, and then that's it, right? You don't need to say, oh, to him and however many other devices there are in the core layer. So every access layer device connects once to the distribution layer, and then the distribution layer bundles all those connections and sends them to the core. Now you see these lines here say typical 4-to-1 data over subscription, typical to 20-to-1. That means that these connections are bigger, right? So for example, each core layer device might take 4 times as much traffic going up as it's going to send down as any one of those links, right? Which makes sense. If we go back to Paint here, you think, yeah, this device, it has one connection to this core, but it has a bunch of clients it has to manage. So of course, it has to have more upstream capacity than it has individually downstream on any of these links. So that's just what that data over subscription there means. Okay, so let's talk about the layers. So the access layer is, again, the outer layer of the campus network, contains all these end devices, PCs and printers, and any extending devices that go onward, like internet phones, wireless access points, that sort of thing. And basically, it's the first layer of defense for network security, right? So any sort of, if there's a physical connection for wired devices or the network password for wireless ones, whatever, it's the edge of the network. It's the client machines. The distribution layer is the interface between the core and access layers. So it handles that traffic between the access and core layer devices, does things, security policy things like access lists, who has access to the core layer. And the fact that it's a boundary layer between the two provides an extra place where policies can be checked. So for example, quality of service policies can be implemented there. Right, all the data coming down from the core, the distribution layer devices can decide, well, what traffic has more priority? What do I send down to access layer devices first? Also, nice thing, enables isolating access layer connections without restricting core layer activities. Okay, so imagine for a second, one of these devices has been compromised and it's the source of a denial of service attack, right? It's basically gonna send in a lot of bogus traffic to try to overload the network. Well, what the distribution layer can do is simply, I'll borrow this into Paint. What the distribution layer can do, let's say you are the dangerous one, right? You're causing some trouble right here. The distribution layer can say, nope, we're gonna cut you off, buddy. You're done, right? And then the whole rest of the system can still work while they try to figure out what's going on with this denial of service attack attempt here, right? The rest of the system can still run. So the distribution layer can operate like basically a shutoff valve and say, nope, nothing for you, while the rest of the system keeps running. So it's good for network security and continuous operation. Now, if you have a small network, right, a small-ish network, you don't necessarily need to have separate core and distribution layers. What you sometimes might do is have what's called a collapsed core layer, where you combine the core and distribution layers into one set of hardware, basically. And that's going to be easier to set up, easier to operate, but again, you lose some of these benefits. But yeah, some smaller organizations might choose to do that to save money. The core layer is the network backbone. So typically very high speed, very high capacity. So if you look at, this sort of capacity, geez, people are loud down in the basement. I got the door open, hang on. We got grandma here watching the kids during their normal daytime school stuff. So that's who you heard. Okay, with this 4-to-1 data over subscription, right? Basically each one of these connections is going to be handle 4 times more data as one of these distribution connections. Likewise, each one of these distribution connections is going to have 20-to-1. So the core layer connections are going to be like 80 times more than your ordinary individual connections. They're going to be, very high capacity. The core layer can handle a lot of traffic because it has to, because it handles traffic for the entire organization. Okay, so high speed, high capacity. It connects these key system resources, especially widely separated ones. We'll see that in some of our network diagrams in a minute. And because the core layer is where all the work happens for the network, basically, it needs to be always available, even during upgrades. Even if you're changing something, reconfiguring something, the core layer basically needs to be always on all the time, or else the network is not going to work. Typically, fault tolerance to help keep it working is available through redundancy. So for example, if you have 2 core layer devices that are communicating with each other, right? So I'm going to draw them here. 2 core layer devices communicating with each other. It might be depicted as a single connection, but in fact, what it's going to be is something more like this. There's going to be like at least one switch in the middle, and they're going to be parallel options for traffic flows. So something like this, which basically means if any of these points, I'm going to circle in red, you know, if this port goes down, this port goes down, this switch port goes down, well, that port goes down, if any one of those fails at any given point, there's still going to be a viable path, right? So if this guy goes out on the switch, well, guess what? I can still route around that. I can use the other switch ports. Okay, so that's why I say fault tolerance via redundancy. There are going to be backup components available in case something fails. So it takes multiple failures, like you know, a fire in this whole stream of hardware, to really wreck things. Okay, so also good practice, you don't want users to connect directly to the core layer. So this sort of point that we talked about a minute ago about like denial of service attacks, if you let some outside users, some access layer users connect directly to the core, you don't have an easy shutoff valve for that, right? Basically, you could disable the switch that they're all plugged into, but that's going to shut everybody down. Or setting up individual switch ports, yeah, that's creates some problems too. But if you let access people connect directly to the core, you lose the ability to easily shut off that connection while still maintaining the rest of the network's operation. Okay. Now in practice, separate core layer is nice if you can afford it. So number one, first of all, there are many fewer connections to manage. In that sense, for every access layer device, if you have n access layer devices, you only need n connections to the distribution layer. So there's n connections. However, if every access layer device needs to connect to every other device in the network, you'd need basically n squared, right? Or, you know, n squared minus n, because they don't connect back to themselves. So for every device in the network would need to connect directly to every other device in the network, that would be a big headache. So in general, right, if you have a bunch of devices, it's easier to connect them all into one switch like this, right? And then everybody has a single connection, as opposed, and say we have all the client devices down here. So if I have 6 here, I just need 6 connections. And the switch here takes care of routing traffic, you know, directing traffic from each of these devices to another one as it needs to. It's a lot easier to set up than if I have 6 devices all in a star pattern, right? And I need to manage 30 connections, right? I'm just going to draw 15 because I'm not drawing the two-way ones. But if I have two-way connections, I double it again. There's going to be a lot more than 6 connections here. What am I missing? Oh, right. Those. You get the idea. I'm sure I'm missing a few here, but yeah, there. Okay. You need a lot more connections. And of course, if the number of devices is more than 6, well, you get, you know, correspondingly more connections. Kind of a headache. The other thing, again, separate core layer, clear boundary against direct user connections, which for security and continuous operation, you want to keep users away from direct connections. Same as with the standard N-tier architecture. You have users go through an application server to get to the database. You don't have them just connect straight to the database. Okay, so those are 3 layers. Now, some different configuration plans, right? They're basically going to be logically the same, although spatially they're going to be arranged differently. So, for example, we have a smallish organization that's all operating out of one building. So they have a collapsed distribution core layer. It's all combined together. Here's the connection to the outside world, so to the wide area network and to telephone services, PSTN, that's basically phone service telecom network. Anyway, so floor 6, access and development, each of these, floor 5 engineering, each of these floors has basically a different local area network, so different access layer devices, and they all connect to the distribution layer, which is bundled together with the core layer. Okay, and then if there are other organizations that need to access this stuff, yeah, they go through some outside connection through a router and a firewall to get to the core layer as well. Okay, but here, again, each floor is a different cluster of access layer devices. But if the organization is bigger, we can apply the same logical setup, right? Again, instead of having each floor be an access layer cluster, each building is instead an access layer cluster. So here we have a data center in the middle, building A for management, and every one of these outside buildings, again, connects through a distribution layer, right? The distribution layer in this case is at each building, and then the core layer is here in the middle in building A. Okay, but again, logically the same. It's just kind of a bigger star setup than this. Here it's all in one building. Here it's blown up to multiple buildings. Likewise, if you have an organization that spans multiple campuses, well, I'm going to grab that image. I'm going to put it in Paint. Okay. Once again, logically the same setup. So over here at the top, this is basically the same thing we had before, right? We have our core layer in the central building, right? It connects to some services block, data center, whatever, but we have distribution layer for each of these buildings. On the outside, right, we have connections to the internet. They can again go through this. If we have another group, right, another campus in a physically different location, it can have the same thing. So again, each building has its own access layer groups, and they go through a distribution layer to the core. But what we see here is that the core is basically set up like this. This is where the core is. So even though the core spans multiple buildings, right, or if I wanted to, let's see, I could have it encompass that as well. This is kind of a core setup too. There we go. Kind of captured it all. So we still have the core. The core is connected to itself, right? But the access layer devices still go through distribution layers. I can mark them in green. These distribution layer connections, right? I'll go through there. So we're setting it up again, same logical setup. We have the core in the middle, distribution layer, and the core is distributed over multiple facilities. The distribution layer, anywhere you connect to the core, you go through the distribution layer to do it. And then all around the edge, you have the access layer devices, like there, you know, there, presumably some in the outside world there, and there, and whoop, and there, and there. And that ring there should, of course, be green. Somehow he got purple, but there he is, he's green now. Okay, and that's it. That's the basic kind of setup. Okay. Questions on any of this? It's a good point to, we're going to take a minute. We're going to absorb think about all the knowledge we've picked up. Questions on any of this stuff? Any stuff that doesn't make sense? Nothing? We're all good? Everybody still tuned in? All right, moving on then. So next thing to talk about, mobile devices versus networks, right? So we've seen a big shift in the last 10 years away from desktops off to mobile devices. So 10 years ago, you went to an organization, yeah, there'd be a lot of desktops people use. Some organizations still use, excuse me, like, you know, UIC, wireless is everywhere there, sure, but the ordinary admin people, yeah, people still use desktops. It's what they have. So anyway, I remember about 5 years ago, my wife said to me, you shouldn't even talk about desktops anymore. Nobody uses desktops. And I said, well, we use them. Their organizations might. They still exist. Anyway, but basic discussion there, thin versus thick applications. So there's two ways to set up an application. One is where the application runs locally on the client machine. For example, I'm running PowerPoint on this machine. It does all the work here. I don't need an internet connection to use it. So that is a thick application, does the work locally. A thin application, though, mostly relies on network devices to do the work. So if, for example, I didn't really run most of PowerPoint locally, instead I connected to a server where it ran, that would be a thin application. A good example of that is, say, Facebook, right? Because on Facebook, you don't install a client application on your machine. You just go to the Facebook website, and all the work that happens, that's happening on Facebook's end, and they send the results of that work to your machine, to your browser. So thin versus thick applications. Now, desktops, of course, are generally more powerful than comparable mobile devices. They have more memory, more storage capacity, can do more CPU cycles, whatever. So they can do more work than a typical mobile device. If you're shifting to mobile devices, that means you're more generally going to rely on thin applications. The mobile devices are not often terribly powerful. They're not going to do much of the work locally. You're going to have some server or other components doing the work. And that means there's going to be more data transfer requirements. If you have a desktop doing the work, it doesn't need that much connection to the network. But if you have a mobile device that's not doing most of the work, then yeah, you're going to have a lot of data going back and forth. Every time you change something, it's going to be sending messages. So other things, mobile service gaps and fluctuations. So number one, mobile devices are subject to interference. Anytime you have a Wi-Fi connection, yeah, there's going to be the possibility that your signals get interfered with by other things, or that there are just terrain obstacles, whatever. We've all experienced a thing where we're wandering around in a building. We have great reception, great connection on one side of the building, not so much on the other. The other thing, all else equal, mobile devices tend to generate more traffic due to repeat transmissions. Anytime something goes wrong, right, they're going to have to resend the message, and that adds traffic into the network too. Another thing, seamless roaming. So if you have multiple devices, multiple wireless access points that your devices can connect to, that means you're potentially going to be sending signals to multiple wireless access points. And that's going to multiply the amount of traffic that's getting sent. So essentially, each wireless access point is going to be receiving multiple copies of the message, and that's going to make more potential for interference. So a simple thing. All right, so I'm going to draw some wireless access points here. Whatever. If I'm a device, let's make a, here's my phone. Give it a little antenna here. Okay, if I'm within range of this, I'm going to be within range of multiple wireless access points, right? And that means if I'm communicating with him, I'm eating up a little bit of his ability to receive messages. If I'm communicating with him at the same time, eating up a little bit of that. But this is necessary in order to keep seamless roaming to ensure that I'm always within range of one wireless access point. It means in most cases, I'm also going to be in range of more than one. So by getting rid of these dead zones, that means in most cases, I'm going to be, taking up space on multiple wireless access points. Even though only one of them is actually going to process the message, they're all going to have to listen and receive it, and it's going to potentially interfere with incoming signals from other devices. Okay. The other thing, mobile use, this is a big thing. Mobile users can cause sudden local spikes in network traffic, right? You may have something going on in your organization where boom, out of the blue, there's like 100 or 200 people all showing up and they've got their mobile devices and it's just a big crush of traffic. You can see this downtown at the metro stations. There's a few businesses that provide free Wi-Fi, like the McDonald's at Ogilvy has free Wi-Fi if you want it. But the problem with that, if it's a busy time at, if it's like, say 9 p.m. and there's nobody there in the station, yeah, you can get a decent connection through there. But if it's rush hour, just forget it. There's thousands of people down there. And even if they're not actively doing something, they're all basically filling up the available wireless space with signals, and you'll have a tough time connecting to, the free one. Okay. That's it for a quick intro for how mobile devices are. Wireless access points. They're, hopefully you know what they are. Most of you are going to have one in your own house. Typically, they're going to be connected to a router or going to be an integral component of one. Once upon a time, you bought them as separate standalone hardware, but nowadays, you buy a router, it has that wireless capability in it. And then the wireless access points router connects to the wired network like anything else. So again, the typical home setup is going to be something like this. You have your wireless access point that, connects to the internet, right, to your ISP. And then inside, you have the option, you might have some wired devices that directly connect into it. Like for us, we got some Orbeez that basically make a mesh throughout our house, if you know about those. So say Orbi devices. You might have something similar, or some kind of Ethernet connection to whatever if you want to go wired. But in most cases, you're going to be using, make some curvy wired signals. Damn it. We're going to try to. There we go. So you have some wireless signals going various places throughout your home. You get the idea. Okay. But within your house, right? Yeah, a lot of people are probably connecting through wireless connections, but wired are a possibility. And then, of course, going out to your ISP, that's definitely going to be a wired connection. Okay, so state-of-the-art wireless standards, they can support tremendously large user groups. The high-capacity one you'll probably see now is 802.11ac. There are other higher capacity ones in the works, but there are older ones you might still have, like 802.11n. They're good enough if you're just a few people in your house. You can manage multiple streaming video connections, but if you try to have like a big video conference, yeah, it's not going to work so well. Anyway, all right. Another thing following up with that, wireless mesh networks. So again, in our house, we have some Orbi devices, which are basically little wireless access points that are local to like a particular floor or even a particular big room. And we use those, and they're all connected with our router downstairs. So a similar thing with this kind of enterprise scale mesh network. Basically, you have a cooperative network of semi-static access points. So these things, I mean, they're kind of like big, heavy suitcases, right? They got the wireless access point. They got a big battery that goes around with them. You can put them wherever you want. You can move them, but they're kind of a hassle, and you don't want to move them unless you really need to. But anytime you have you need local access or capacity requirements, they change. For example, some building is having a big conference over here, so you pick up some of these access points, move them around over to this side. You can have extra capacity for people. The difference is, in a typical wired network, you're not cooperative, right? Here, for example, this mesh point, I'm gonna lift this one again, put it in paint. Whoop. Damn it. Here in this kind of setup, okay, this guy at the end, let's circle him. He both sends data, right? So sends data to the wired network, but also carries data for, outward wireless access point, right? So this guy over here, he's carrying data for him. This purple guy, anything he wants to do has to go through the red guy and vice versa. So again, unlike in a typical wired network, everybody would be connected to the router or connected to some sort of hierarchical set of switches. Devices won't generally carry traffic for each other. But in this kind of mesh network, yeah, they need to do that. That's part of the setup. So when I say cooperative network, that's what I mean. I mean that some of these devices closer to the wired network are going to have to carry traffic for others further out. Okay. Similar thing, you can set up some kind of equivalent of the hierarchical network with mobile devices. So essentially what you have there is, up at the top, they have what's called a mobility oracle. This is Cisco's converged access network design. So this guy, he governs a set of basically big wireless access points. Each one of these is going to govern a set of other wireless access points, right? Until we get down to the end of the individual routers. So when people move from one access point to another, they get governed by a different group. So if I drift from, say, peer group A1 over here to peer group A2, I'm still going to be governed by this guy, and my traffic's going to go up through him, but I'm going to go through this access point instead of one of these access points, right? So again, it's basically setting up a hierarchical system design with more or less parallel traffic flows, except it's with a wireless design. So there's some sort of organization here that says, yeah, preferentially, if you're around this guy, you're going to send traffic through him. If you're around this guy, you're going to send traffic through here. And that's what it's trying to do, is trying to send traffic more efficiently. For example, if I'm over here, even though this peer group 2 or even the subdomain A connection might see the signal, it's going to ignore it. It's going to say, you're not part of my group, you're part of B, and only B is going to handle your traffic. That's how the traffic flows get implemented. Okay. Now, the rest of this that we're going to talk today is network communication layers, routing protocols, stuff like that. So typically an enterprise network is going to be a connected group of local area networks. And across local area networks, communication happens at the network layer. So if you have two local area networks that want to communicate with each other, that happens at what's called the network layer, or level 3 of the layer 3 of the OSI model, and essentially through routing. Within a LAN, communication happens at what's called the data link layer through either switched or direct connections, right? So if you guys remember our internet architecture layer, we talked about these layers. Yeah, here's how they're implemented. We'll draw a quick picture. Very quick. So suppose we have 3 clients. Here's a routed connection. You know what? We're going to do the Cisco convention. We're going to draw that red. Okay. And then, so here's a router, and connected with switches going onward. Okay. Have that in red. Okay, over here, router. Okay, so what happens if one of these devices, is trying to send a message within its network? It's all going to happen at level 2. It doesn't really go through the router to another network. It just, the message goes up to the router, and the router looks at it and says, oh, the destination for this is in my network. Great, I'll just kick it back down this way. On the other hand, if you go to another network, then it has to be handled differently, right? It goes from a device here to the router, and the router looks at it and says, oh, the device, you know, the destination for this is not in my network. I'm going to send it onward to this other router that I'm connected to. That router receives it, looks at it at the data link layer, says, well, I am the next recipient for this packet, but when it goes up to the network layer, it looks at that and says, but I'm not the final recipient. Well, the final recipient is somewhere here in my network, so I'm going to pass it on that way through the data link layer. Okay, that's essentially the process, which we talked about the other week. So networks use 3 basic addressing schemes. Number 1, they have a public IP address. That's the network address to the outside world. Number 2, they have a private IP address, which is the address for a device in the network. They also have a medium access control, or MAC address, that is used to identify machines at the data link layer. So essentially, each network, each subnetwork manages the list of all its known connected devices. So every, you know, governing device in the system, for example, the router knows all the devices that are connected to it. So it knows whether it has that particular IP address local to its network or not. Okay, but the point is, just like there are 2 separate layers for checking this end-to-end routing that happens at the network layer, there's also MAC addresses that are used to identify devices that are operating at the data link layer for individual packets. And the reason essentially is so that the layers can be separated and run on different hardware. It wouldn't make sense to use the same addressing scheme for both of those. Okay. So Ethernet is used for wired connections. It's a set of standards that's grouped under 802.3 of the IEEE code. That's just, if you ever see that, that's for wired connections. And it works at the data link layer within LAN. So these direct connections between devices, that's at the data link layer. It's not true routing. It's just data goes in one end, it gets kicked out to the other end. And of course, it's widely used in LANs with static or semi-static configurations, right? If you're not changing the setup very often, then usually wired connections are great. They're high capacity. The only downside is, you know, your devices are pretty much fixed in place once you deploy them. Fairly high data rates, right? Generally much higher than comparable era wireless connections. Reason is, in Ethernet, each cable is a separate channel, right? It's a lot easier to prevent interference. You can have narrow bands of bundles of cable inside that carry the data separately. With wireless connections, it's all going through the air. There's a lot more potential for interference. In fact, even though this is what we see in our house, right, is the top is like 40 and 100 gigabits per second, there are ridiculously fast ones out there that have been tested. For example, in 2014, these guys, let's see if this is still here. These guys set up a ridiculously fast connection. Here we go. Wow, that's a slow connection. Okay, so over in the Netherlands, researchers demonstrate record data transmission over specially fabricated fiber. So record high, 255 terabits per second, right? So more than 1,000 times faster, you know, several thousand times faster than your ordinary Ethernet connections. And this wasn't like a little connection that was like 2 millimeters apart. This was like they did it over a stretch of like a mile and a half, give or take, right? So yeah, they could get this much faster if they wanted to. It's just, you know, at this point, it's not really necessary and it's more expensive to do it this way. But yeah, for sure, much higher data transmission rates are possible than what we see, or than what you have in your house right now, or even what the standard internet fiber optic cable backbone runs. Okay, so Ethernet. Key attributes, every Ethernet device has a unique hardware-dependent MAC address. So when the device is manufactured in the first place, every manufacturer gets a block of MAC addresses, and one at a time as these devices roll off the assembly line, it assigns the next one up to each device. Now we know how this works as far as message delivery. When a device receives a packet, first receives it from the physical layer, then looks at it at the data link layer and says, is this for me? If the destination address is me, then I'm gonna keep it and pass it up to the network layer. The network layer is then gonna look at it using the IP address and say, am I the final destination for this? If yes, I keep it, I process it ultimately up to the application layer. If not, I kick it back down to the data link layer to get forwarded on to the next device in the series. Okay, anyway, so that's how the MAC address is used as far as the implementation of the data link layer. Now, Ethernet packets, essentially they're sent in as frames. So you have all the message, which is what's called the payload, but there's some extra wrapper stuff around it. So first of all, it starts with a preamble, so a set of ones and zeros. So basically D, 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 which gives the receiving device a chance to recognize, oh, here's an incoming packet, right? That's the signal that it's looking for to recognize that the packet is coming in the first place. Then it has information about the destination and source address, right? So it says, who is the destination for this device? Then it has length for the packet size, right? So how much information is in there, and that's something that the recipient device needs to recognize when the packet is done transmitting. Then finally, the actual packet data, and at the end, what's called a cyclic redundancy check. So basically a kind of checksum, so that all the numbers in the payload can be added together, and then they go through some numeric conversion process. That number gets attached to the end of the packet. So when the receiving device gets that packet, it does the same computation. It takes all the data in the payload, runs it through the same set of calculations. If it comes out with the same number as the CRC, cyclic redundancy check code, then it says, okay, yeah, I'm gonna assume I got the packet transmitted correctly. Okay, so basic for this, yeah, Ethernet devices, every device has a unique hardware-defined MAC address, and Ethernet packets have these additional details wrapped around each packet. Okay, now remember, Ethernet is only used for wired connections, traffic within a network. So if the packet recipient is found locally, right, it's in the same local area network, then you send it to that local machine through the router, and the router directs it to it. If the packet recipient isn't local, then the packet goes to a gateway, right? It goes through the router out to another network. And all that is not going to happen at Ethernet. That's going to happen on some other kind of connection. So for traffic across networks, Ethernet is used to get the packet out of the sender's network, and once it gets to the recipient network, to move within there. But for other schemes, we have what are called routing protocols that get the packet from one router to another. Okay, so routers are the hardware that move data between networks, right? So again, from one LAN to another, or from one LAN to a wide area network, a WAN. And they operate at the third layer of the OSI model, so the network layer, or the internet layer for TCP. Basically, routers are used to separate a network into multiple what are called broadcast domains. There are various times in a network where the router wants to send a message to every device in a network, or one device in a network needs to send a message to every device. For example, if I'm a device in the network and I want to find out if some other device is actually in the network, I can can send out what's called a series of broadcasts. I can transmit to every node in the network and identify if someone is there. So at some point, whoever is the intended recipient for that one can send a confirmation message back and say, okay, here I am. But if broadcasts are happening fairly often, devices are connecting, reconnecting, trying to find other devices, you can have an unpleasant amount of this broadcast traffic leading to what are called broadcast storms. So anyway, the bigger the network is, the more likely that kind of broadcast is to occur, and the broadcasts, when they happen, are going to involve more devices. So if you had a really big network like internet scale, and it wasn't separated by routers, these broadcast storms would be a total nightmare, right? That's all the network would be able to do. It wouldn't even be able to keep up with that. So routers are used to break up the networks because these broadcast attempts only happen within the domain of the router, like within a local area network. Now, compared to switches, routers are pretty smart. They can do more stuff, but they're also much more expensive. So key things they can do, number one, choose the optimal path for data. So they can look at things like simple distance, like the number of connected devices it has to go to, or looking at how busy individual links between devices are. So in various ways, routers can try to send data along an optimal path according to whatever metrics have been built into it. They can also provide quality of service management across networks. So they can prioritize which applications are important and send data for those applications first. Switches are kind of dumb. They often don't do that. They often just, data comes in, the switch echoes it out. They can do it within a network, but they can't do it across networks. Once data gets into a network, then the switch is just going to have to, send stuff onward. Okay. So a basic question, how do nodes learn routes? So we're going to talk about a couple of these models, and that'll pretty much close out the lecture here. So we're getting close to the end. All right. So basic routing models, again, how do they learn it? Well, here's the assumption. In a hierarchical system, either the address is contained at or below the current level, right? For example, it's in your local area network. If not, you've got to kick the request up to the next level. For example, in our typical Cisco layered design, if it's another access layer device in my local group, then yeah, I can just send it up to the distribution layer and it'll go back down. But if I send it up to the device at the distribution layer and the distribution layer says, nope, this device isn't part of my group, then it kicks it up to the core layer. And then the core layer is going to have a list of which distribution layer has this device, and it echoes that message onward. So the address is either contained locally at the current level, or the request gets forwarded up to the next one, and that device that's one higher will hopefully know where to send it. And individual nodes, they can get updates letting them either know what the next best hop is, where's the best place to send the device, send the packet, and in some cases the complete route. So let's make a little routing map. Imagine if, right, we're going to have a bunch of routers here. We have a bunch of options to get to where we're going to do. Here's our source, and here's our destination. And we want to know, given the potentially large number of routing paths that exist, how should I get my packet to where it needs to be? So these routers are connected to each other in some sort of weird mesh going on there. And there's going to be a bunch of different possibilities for how to actually send the data to where it gets here. Now, depending on what's going on in the network, right, one or more of these might be optimal, they might not, we don't know. I'm going to let's pull that. So for example, it might make sense to send a packet here. Maybe you identify that this is the fastest path, or maybe you identify that that's the fastest path, or even that, right? We don't know going in what the fastest path is going to be. So there are different schemes for that. Now there are a whole bunch of different routing protocols. This isn't a computer science course, so we're not going to get too deep into it. But there are different ones, and they suffer different kinds of scalability problems. They tend to, different routing protocols will fail in different ways as the system gets too big. So number one, how often information updates have to be transmitted. So if there's some change to the configuration of the network, the more often the network is checking for those changes, the more often things are going to get slowed down because of that. Number two, the size of the information update messages. So if it's a very big network where things are changing a lot, the routing protocol is going to have to periodically send these update messages, but they're going to be very long because they're going to comprise data of a whole bunch of different machines. And then the number of times each update message is transmitted, right? So if devices are just transmitting this information periodically to their immediate locally connected routers, it's not going to be that big of an impact. But if I'm trying to do some global scale update where basically every router is going to send its complete list of updates to every other connected device, then that's going to start to fail at a relatively low scale. It's just going to be a lot of extra traffic injected to the network. So there are different ways to do this. There are all kinds of different schemes about how and where and what to send as far as updates. And yeah, if you go after a master's in MIS, you may learn more about these things. I used to cover it when I taught 520. Anyway, but the two basic families we're going to talk about, link state and distance vector. And that's going to close out today's lecture. So in a link state routing protocol, what we have, routers periodically share information about the states of their links with other routers. So typically something like latency. Okay, so we're going to write this here. Link state routing protocols, not surprisingly, devices share information about their links, right? Typically, you know, speed and available capacity. So information like that, is this a busy link? Is it not a busy link? So every one of these devices, for example, if we pick this red guy here, he is periodically going to share information about this link and this link and this link and this link. Okay, because that's all he knows about directly, but that's what he knows. This link information percolates through the network, right? So it doesn't generate a broadcast storm that when this guy updates something, he immediately sends it to everybody in the network, but it does eventually get shared from one device to the next, and then he passes his knowledge on to this one. It does, over time, percolate through the network, and eventually, every device has a fairly current idea of the entire network state, right? Basically, for any given link in the network, every device is going to have a reasonably recent update on how good it is. So the basic operation routing happens like this. When a device is ready to send a packet, when a device sends a packet, it sends it to the next hop on its best path. So it simply says, you know, this source, based on my knowledge of the entire network, I'm going to say this one is the best hop to send it to. It's like the next hop on the shortest path that I've identified. So I'm going to send it to him. This guy, when he gets it, he's going to do the same thing, right? And each subsequent router does the same, right? That's how that's going to work. The next router on the path is also going to have some idea of what the best path is, and it's going to send it to what it thinks is the next best hop, right? The next hop on the best path. And eventually the packet will get to its recipient that way. Okay, so the way the advertising works, devices send out their knowledge of their locally connected links. Each one of those has a timestamp attached so that, you know, a more recent link update will override the information from an older one. Okay, so router receives an advertisement with a higher sequence number. It forwards that to other routers so that everybody can learn the more recent information. And if your network is set up as a spanning tree, which basically means, you know, a big tree so that there's only one path for between any pair of devices, the advertisement is going to be quickly sent out to all routers, you know, that are connected. So as far as routing, each router builds a map of connections to all the routers. Sending router estimates the best overall path and sends the packet to the next hop on that best path. And each subsequent router does the same. Each subsequent router receives the packet, says, oh, this packet is going to such and such destination. I have a map of the network. I know the best path from me to that destination. I'm going to send it to the next device on that path. Okay, distance vector protocols are a little different. So distance vector, I know we're running on time. We'll get done. This is the last slide, so we just got a couple minutes. Each router maintains a table of the shortest distance to all other routers. And again, this could be a simple hop count for how many devices it has to go through to get to the destination, or it could be other more advanced performance metrics like time. Periodically, routers advertise their tables to their neighbors, right? So here's the information in a distance vector. Routing protocol. Each device initially knows who it's connected to directly, right? So single hop. That information can be shared with other devices who will then know they are 2 hops away from the device. And so on until all distances are known to all devices, right? So this information gets periodically echoed on. So imagine, right, we give each of these a label. You can be A, you can be B, C, D, E, F, G, and H, and I here at the end. Okay, so H knows H to I is 1 hop, right? They're separated. Since F and G are also 1 hop away from H, so F to I is known to be 2 hops, and G to I is also known to be 2 hops, right? Since F is directly connected to DE and C, D, and E, we know C to D or C to I is going to be 3 hops, D to I is going to be 3 hops, and E to I is also going to be 3 hops. Okay, we go back 1, we say A to I, of course, is going to be 4 hops, right? Because A is connected to C and E, so it's going to be 3 plus 1. So when A gets a packet from the source that's going to I, A looks and says, oh, well, E is 3 hops away, C is 3 hops away, B is 4 hops away. It's going to send it to either C or E, and they're going to do the same thing going onward. Okay, that's how distance vector does. So each of these devices, they're not going to send information necessarily about the state of the link so that each device builds a complete map. What they're going to do is just give an estimate of how far away they are from the destination. And so then A, when it gets the packet, it's going to send it to the next hop on what it thinks is the shortest path, right? So a device receiving a packet will send it to the next hop on its best known shortest path. Okay, that's how distance vector works. And again, periodically these devices advertise their tables of lists so that each device can check and say, oh, has anything changed lately? So, information sharing, each router keeps a table of shortest distances to other routers. They periodically advertise them. If a router learns that a neighbor's found a shorter route, it might update its own table with the shorter route plus the distance to that neighbor. Over time, each router eventually has a fairly current table of the shortest distances to all other routers through particular neighbors, right? So it knows if I send it to device X, it might be 6 hops to, destination Z. If I send it through Y, maybe it's only 4 hops to get to Z, but they're going to keep this complete list. And for routing, sending router sends the packet to its neighbor on the shortest path towards the destination. So when I receive a packet, I look at my list of connected routers, I pick which of them has the shortest path to that destination, and I send it onward that way. And again, that neighbor is going to keep forwarding it the same way, and eventually it gets received at the end. Okay, so these are the 2 big families of routing protocols that are used in ordinary networks: link state routing and distance vector routing. and you should understand basically how they work. Okay, but this concludes the lecture as such. So I'm gonna stop the recording.